All right, hi everybody. I've been having trouble with my Screencastify. I don't know what's going on. I'm sorry that the previous screencast cut off midway through, but I'm just going to pick up where I left off. Unfortunately, I'm in my house now. I'm not sitting out on my deck anymore, which makes me sad. Okay, so I'm going to flip my Chromebook over again. I hope that's not what caused my problem. So here we go, flipping it over. And now you're going to look at my ceiling instead of the beautiful outside. It maybe had something, well, okay, never mind. So I'm going to go ahead and draw the energy profile. So number 3 says, draw a basic XY graph. I'm going to grab a good color here. And using the actual values, construct an energy profile for the reaction in number 1B. So let's go back and look at what number 1B was one more time. I'm going to bring that back up. And so, whoops, I went too far. 1B was the 2H2S plus 3O2 plus 2H, blah, 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 blah. So that's the information that we're going to be graphing. So here's the, down here is where we have the kilojoules per mole that are at the end of it. Okay, so I'm going to go back and I'm going to make the graph. So we are going to draw, and I'm sorry that I don't have fabulous handwriting like some of you do. And along the bottom of our graph is going to be time. And along the side of our graph is going to be energy. And in fact, it's kind of a weird thing to have to graph this because it's going to be negative. It's all negative. So you could imagine like 0 would be up here. And this part of the graph, this part going down, that's all negative. I'm not going to draw it that way right now. And I'm not even going to put the 0 there. But just to be aware of that because we're looking at negative values right now. So let's just say the starting value for the the reactants. Gosh, that's hard to say. So we'll put a line right here. Those will be our reactants. And for that particular problem, the reactants, there were 2H2S plus 3O2. Those were the reactants. If you hear any growling in the background, it is definitely not me or my stomach. My dog is growling and she might start barking. So just forgive me for that noise. And they're starting right here. They're starting at a level of negative 41.26. Is it kilojoules? I think it's kilojoules. Is that right? I don't remember off the top of my head here. Yeah, kilojoules per mole. Okay, so that's the level that they're starting at. I'm going to make this a little bit longer because I drew that so fat. And then we need to achieve a certain, what they call activation energy to get the reaction to move forward. And then they fall down to here. The lower level is at a minus, and this was the answer at the end of it. Was it a minus 1165.32 kilojoules per mole? I'm not going to write that right now. And those products that we had at the end, it was 2 water molecules and 2 sulfur dioxide molecules at the end. So what this is asking us, it's asking us to draw the activation energy. So remember that the activation energy is the energy it takes to move from this level up to get the reaction to occur. So that's the activation energy. And we're going to say that that activation energy, because they just gave it to us, is 350 kilojoules. Then we want to calculate, and this is what we've been doing throughout this whole worksheet. We want to calculate this distance here. It's the change in energy, the change in heat, the change in enthalpy between the beginning of the reaction and the end of the reaction. So that's our delta H of formation, and that was the number minus 1124.06 kilojoules per mole. And that was for the molecules at the end. So that's the difference between the difference between the reactants and the products. That's hard for me to say. The difference between the reactants and the products, that's the final answer right there. Okay, I hope that all made sense. I didn't speak very clearly, but hopefully that made sense. I'm going to go ahead and scooch on to the next problem. All right, for ethane thiol, what we're looking at here, they already gave us the answer, but ethane thiol, which is this one right here, we don't actually know its standard heat of formation, so we're going to solve for that. So it's just a little bit of algebra here. So we're going to set it up. I'm going to choose a new color maybe today. So we're going to say negative 3754 kilojoules equals, and now we're going to put the products first. Okay. Oh, and I forgot to balance it. I'm sorry. And the balancing on this one, let me see if I can remember. I've got it all written out. Yeah, the balancing is kind of a hassle on this one because it's a big one. So there's 2, and then the O2 is a 9. The CO2 is a 4, the SO2 is a 2, and the H2O is a 6. There, now it's fully balanced. That's a difficult one to balance. Okay, so now I'm going to take the products. So these are my products here. I'm going to do 4 times, and then I look it up on the table for carbon dioxide, and it is a minus 393.59. And I add that to 2 of the SO2s, and the SO2 are minus 296.83. And I add that to 6 liquid water. It's super important that it's liquid water because gaseous water is different. On the table, you might see CR, and that stands for crystalline, which means solid. So if you see that, sometimes that's what that is. And that's a minus 285.83. And now I have all of that long part, that represents the products. And now I'm going to subtract the reactants. The reactants, it's 2 times ethane thiol, and that's what we don't know. So we're going to call that our X. And conveniently, yes, this problem was chosen specifically because it was easy. We do 9 times oxygen. Oxygen is an element, so it has a heat of formation of 0. So we don't have to even include it. So now we can just focus on the 2x here. So we do all the math, and then we divide by 2 to solve for x by itself. I'm not going to go through all the math for you, but you should end up with x equaling negative 64.485. Gosh, I have not been paying attention to sig figs. I always pay attention to sig figs. I think there are actually a lot of sig figs in all these, so maybe I've done it right. And then this would be for the ethane thiol, so H5SH. And that is it for problem number 4. All right, now problem number 5, exactly the same. They give us the ending, and they're asking us to solve for P4S3. So let's go ahead and balance that. I'm going to switch colors for now. So to balance it, we need 8 oxygens and 3 sulfur dioxides. And now we set it up the same way. Negative 3677 equals, and we're going to do the products first. So right off the bat, we've got our product that we are unfamiliar with. Oh, sorry, the product we do know. I was trying to figure that out. The product we do know. So that is a 1. We don't have to multiply 1. And you can look it up on your table. So I'm doing P410. So you can look that one up on the table. Give me just a second to find it on my table. And it's a minus 2984 plus, and then there are 3 sulfur dioxide, so 3, and then sulfur dioxide we've already seen a whole bunch of times today, minus 296.83. And that, ladies and gentlemen, is our products. We're going to subtract our reactants. That would be just a 1x because it's just a 1 in front of the P4S3. Plus, and then we have 8, and conveniently again, oxygens are 0 because they are an element, so we can basically ignore them. So now we set up this equation to solve for x. We're just solving for a single x, no coefficient in front of it this time. So we should end up with an answer of minus 197.49 equals x. There we go. I had to turn my positives and negatives around. But that is the heat of formation for P4S3. And we've solved 2 of them. All right, for the last 3 problems, this really brings it into biology, which I kind of like tying it back into biology. So it says the following reaction is the body breaking down the carbohydrate glucose. So glucose is what plants make during photosynthesis. and its heat of formation is a negative 2,803 kilojoules. So it says, or the change in enthalpy is the best way to say it, but how much energy is generated by breaking down 1 gram of the glucose? Hint, this is just a simple Stoich problem. 2,803 kilojoules is for 1 mole of glucose. So we're going to use that as a conversion factor. So what would it be for 1 gram? So let's write it the same way we would have done our stoichiometry. So we have 1 gram of C6H12O6, and we're going to turn that into moles. So we're going to do the molar mass, which is a hassle to add up, and I will add it up for you. 180.15 grams of C6H12O6. Okay, so now we have put grams on the bottom. That's not what I meant to hit. We put grams on the bottom, so we just got rid of grams, and now we're in moles. So now the next thing we're going to want to do, whoops, wrong color, we're going to multiply by, we're going to put 1 mole on the bottom. Actually, I forgot something super important. My apologies. We forgot to balance the equation. That is very important. So let's make sure the equation is balanced. So it is actually just 1 mole of the glucose, and then 6 moles of the oxygen, 6 moles of the carbon dioxide, and 6 moles of the water. So this number on the bottom of our conversion factor is 1 mole because it's 1 for the coefficient. So 1 mole, and then it is minus 2,803 kilojoules. So our moles have canceled out. Moles have canceled out, and we are left with the unit of kilojoules. So now we multiply it all out. 1 gram times 1 mole times 2,803 negative, divided by the mass. And when you type that all into the calculator, we get a negative 15.56 kilojoules. So the question was, how much energy is generated by breaking down 1 gram of the glucose? And the answer is 15.56 kilojoules. We are down 15.5, so that means it's an exothermic reaction. All right, now let's move on to the next page. We're going to, instead of looking at a gram of glucose, we're going to look at a gram of fat. And I'm on question 8 there. Oh, no, that's cheating. We got to delete all this. No, this is supposed to be here. You weren't supposed to see that. Look away. Pretend like you didn't see any of that. I thought I had deleted that all. Okay, so it says the following reaction is the body breaking down the fat, glycerol, and no, I have no idea how to say that, trimyrostate. I don't know. We need to start out by balancing the equation. This one is a crazy one to balance. It's actually not that hard, but it's funky numbers. 127 oxygen. Carbon dioxide is 90, and water is 86. So what's important as we do this problem is the 2 in front of the fat, because that means that this number is for 2 moles of the fat, not 1 mole of the fat. So that's relevant when we finish up. So we're going to start it in exactly the same way that we started the last problem. It's a simple stoichiometry problem. So 1 gram of C45. Holy cow, have we ever seen such a big molecule? H86O6, and we want to convert that into moles. So we're going to put the grams of it on the bottom. And yes, oops, that is some messy handwriting, KJ. It's 45, H86O6. Yes, I will add up the mass for you if you're taking the time to listen to this. The mass is 700. Wow, 23. Oh my gosh, KJ. 723.177 grams. Okay, so our grams have canceled off, and now our unit is moles. There are 2 moles of this fat, 2 moles of this fat for every negative 55,640 kilojoules, and we multiply it all together and divided by the mass. So 1 gram times 1 mole times the kilojoules divided by 723. Probably shouldn't even be a negative 55,000, but that's fine. We'll go with that. And so what we end up with for a final answer And again, if it were positive, that's not a problem, but we're just showing you that this is an exothermic reaction. So that's how much energy is released by breaking down 1 gram of fat. So now the final question on this is for us to compare the fat to the glucose. It says, in terms of energy, explain why the body stores fuel as fat instead of as glucose. So take a look at glucose. This was how much energy was released from 1 gram of glucose. This is how much energy is released from 1 gram of fat. So that's why the body stores extra energy or stores fuel as fat. We are able to store much more energy than carbs or glucose. Okay, and then the last question says, data commonly given by nutritionists say that your ratio of energy for fat to carbohydrate should be approximately 9-4. Does your data from 5 and 6 match that? Was it 5 and 6 or 7 and 8? I probably was supposed to change the number on that, wasn't I? My data from 6 and 7, that's what it was. This is supposed to be a 6, and this is supposed to be a 7. Yeah, I should have fixed that. Sorry about that. Let's go ahead and change colors. So let's take a look. So we're going to basically do a ratio. So the ratio, the fat to carbohydrate. So fat is going to be on the top. So when we did the calculation, the fat produced or had released, that's what I'm looking for, negative 38 or 38.47 kilojoules. So 38.47 kilojoules were released, whereas the glucose released 15.56 kilojoules, which if you divide the two, we get a ratio of 2.47. And 9/4, which is what they're talking about in the problem, gives us a ratio of 2.25. Now we could do the statistics and see if it's significantly different, but for our sakes, we're going to say these are fairly similar ratios. So does your data? We'll say yes, fairly similar ratios. And peeps, we are all done with this. Let me know if you have questions. Hopefully this one recorded correctly. All right, have a great one. Whoops, that wasn't supposed to happen. Trying to get this to shut off now.